Hey ChemStars, we ran out of time on our last video, so we're going to pick up at the bottom of page 3 and use that as a review. So we learned about alpha radiation, which is basically a helium nucleus, and it's made up of 2 protons, 2 neutrons, has a mass of 4 and a charge of positive 2. Your skin can block it, so not really the most dangerous particle we'll look at. Then beta radiation, we got 2 types. We have the beta particle, which is essentially an electron, and we have the positron, which is kind of an inverse electron where it has a positive charge. So the beta particle, the electron one, has a charge of -1, and the positron has a charge of +1. The mass for both particles is 0. It's so small, it's essentially 0. And a common source would be from radioactive carbon-14, or things that have smaller nuclei compared to what we've seen. Penetrating power for this one is medium. If you look up at your notes, about a 1-inch thick wood door can block beta radiation. And so the shielding could be a door or even some walls in a well-built building. Okay, let's look at gamma radiation. So it is pure energy. It is not matter, it is not a particle, it's a form of electromagnetic radiation. The symbol is the Greek letter gamma, which kind of looks like an upside down cursive L. There is no charge. There is no mass. A common source is it goes along with the alpha and the beta decay, so it comes along with either type of those. The penetrating power is high. You need concrete, several feet of concrete, or several feet of lead to block that. Okay, let's go over to page 4 now. So we're going to look at nuclear transformations. So section 1, nuclear stability and decay. We want to revisit the definition of radioactivity. It's the process by which an unstable nucleus emits one or more particles or energy in the form of electromagnetic radiation. So keep in mind that everything except hydrogen has 2 or more protons, and at least 1 neutron. So there's particles that can be given off. So let's think about what causes that instability. It's the protons and neutrons in the nucleus. So think about it. Protons are positively charged. They can repel each other. Neutrons have no charge. They don't repel each other. So if you have a positive charge right next to a positive charge, they will repel. Just like if you've ever tried to force 2 ends of a magnet together that are the same, they'll repel each other. So why do atoms stick together? Why don't they go flying apart? Those neutrons inside the nucleus act kind of like a buffer. There's also something called nuclear strong force. It's an attractive force between protons and protons, between neutrons and neutrons, and between protons and neutrons. That's all you really need to know. I'll post some more things on Google Classroom if you want to get into it more in depth. So let's move on to what the strong force means. So if the strong force is greater than the repulsion force, it's stable. So that means there's more cohesive forces than like the repulsive forces. But when that strong force is less than the repulsive forces, it's unstable. So they will push apart, the protons and neutrons will push apart, and it will emit radiation. More neutrons can help hold the nucleus together, but there is a limit. So why the largest elements are unstable and radioactive? It's because we've reached that limit. Remember that atoms are 3-dimensional. So we're trying to pack all those protons in together and they want to repel. And when you go into 3D space, you got to keep adding more and more neutrons to act as buffers. So what is the limit? There are more than 1,500 different nuclei known. Only 264 are stable. So the big percentage of them are actually unstable and radioactive. That stability depends on the ratio of neutrons to protons. If you go to your textbook, your e-textbook, it's in Chapter 21, it's figure 1.2. You can find a bigger version of this chart we're going to go over next. So this is called the band of stability. And if we take a look at that, you can see that with your smaller atoms, the band of stability is about 1 to 1 almost. So if we focus down at this end, you can see that it kind of is going up 1 proton, 1 neutron. That rate of change, that slope is 1. Every time we add a proton, we got to add another neutron. And you can kind of see that on the periodic table. Like helium has 2 protons and 2 neutrons. Most forms of neon have 10 protons and 10 neutrons. But as we start to get to this part of the graph, you see that the rate of change accelerates. Remember what I said about having to pack all those repulsive protons together in 3D space. We need to start putting a lot more neutrons in to get them to stick together. So as this curve goes up, we have to add more and more neutrons. So what does the dotted line in the graph represent? It's the band of stable nuclei. So that is your answer for A. What is the approximate ratio of neutrons and protons for neodymium? Atomic number 60. So if you go to 60, read the graph, and right here, the ratio is about 1.3. And describe, how does the neutron to proton ratio change as the number of protons increases? Well, let's look at some of those slope values. It starts at 1, then we've got a slope value of 1.2, then we've got a slope value of 1.3, and then we've got a slope value of 1.5. We can see there's an increasing rate of change there. So the more protons there are, you need a lot more neutrons. It is not linear. That graph is looking almost a little bit exponential. And at what atomic number does the ratio stop being 1 to 1? So where do we get this point of inflection? It looks like it's starting somewhere kind of around atomic number 30, but we'll have to look at the bigger graph in our textbook to see that for sure. Okay, so let's try and apply this. What does all this mean? The neutron to proton ratio determines the type of decay that occurs. Too many neutrons? That means there will be beta emission. Too many protons? There'll be electron capture, where it adds an electron to a proton to create a neutron. So we have an electron, we put it with a proton, and we end up with more neutrons. All nuclei that have an atomic number greater than 83 are radioactive. So everything greater than 83 is radioactive. They have too many protons and too many neutrons to be stable, and most of them will undergo alpha decay. So this is an important section here in your notes. Okay, let's go to page 5. So we're going to look at transmutation reactions. So transmutation, that's a fancy word, and all that means is that the conversion of an atom of one element to an atom of another element. That's pretty much alchemy, what all the ancient alchemists were trying to discover, turning lead into gold. Kind of happens during nuclear reactions, but you wouldn't want any gold that's made from that. So let's look at our first example. It can occur 2 ways. Natural, there will be one reactant, and it is spontaneous. So for example, we've already looked at some things involving carbon-14. Here's how carbon-14 is formed. Nitrogen-14 will decay, it's radioactive, will decay into carbon-14 plus a positron. There's a second way, and that is called artificial, man-made. There will be 2 reactants. That means that some human has bombarded the nucleus with a particle, usually an alpha particle. So here's what Rutherford did. Rutherford took nitrogen-14, he shot an alpha particle at it, and he got fluorine. Chadwick discovered the neutron in 1932 by taking beryllium-9, shooting an alpha particle at it, and getting carbon-12 and a neutron given off. So there's 2 reactants. One of them has to be a particle that has been bombarded or shot at the nucleus. And we also have Irene Joliot Curie. That was one of Marie Curie's children, made the first man-made radioisotope. It took aluminum plus an alpha particle and got phosphorus and nitrogen out of there. So the important thing here is that there are 2 reactants that we can identify. All the other ones that are natural will only have 1 reactant. So let's take a look at what the transuranium elements are. So elements that are past uranium, they all have an atomic number above 92. So uranium's atomic number is 92. You can find naturally occurring uranium, but everything above that has to have been made somehow. So let's look at our first example. Uranium-238, if we add 1 neutron to that, we get uranium-239. It is man-made. once uranium-239 exists, it will spontaneously decay. So this one will spontaneously decay. So that's why there's only one reactant. It will spontaneously decay into neptunium plus a beta particle. And then if we have neptunium, it itself again will spontaneously decay. We'll get plutonium and a beta particle. Okay, let's go to the next page. So for our next I can statement, it says I can predict the products of alpha, let's try that again. I can predict the products of alpha, beta, gamma, and positron decay. So the main thing is we're going to try to predict and find what is missing. So here's some observations that we should make. In a nuclear reaction, like I hinted at before, atomic number and mass number are conserved. So that kind of goes back to our laws of conservation. We must conserve atomic number. What we're really conserving is charge. And for the mass number, we're conserving total mass. So this is a generalization. In reality, a small amount of mass is lost, which is then converted to energy. And that also can be a way that we get heat out, light out. Maybe some of that will be the gamma radiation. So here's an example. If we have uranium and we add a neutron, we'll get uranium-239. Treat that arrow like an equal sign. And if you add up the mass on the left, you'll get 239. Add up the mass on the right, you get 239. That checks out. If you add up the charge on the left, we've got 92 protons and no protons here. On the right, we got 92 protons. That checks out. You can use this to determine unknown elements or particles. Recall, alpha decay emits alpha particles. Symbol is 4,2 alpha. Beta decay emits beta radiation. 0, -1, beta. Positron emits positron particles. 0, +1 beta. Neutron decay emits a neutron. Mass is 1, charge is 0, and we have a neutron. An artificial transmutation will always have two reactants. You have to start this one by shooting something at the nucleus. So I'm going to do a couple of examples for you. Then I'm going to ask you to pause the video and then come back and check your work. Okay, so let's try and look at these ones right here. So remember, treat all the arrows like they're equal signs. And let's look at these first couple. Okay, so on my first one, I've got aluminum plus helium. So if we look 27 and 4, mass is 31. On the right, the mass is only 30. So what's missing? A mass of 1. Check out the charge. We've got 13 and 2. So that means I've got a mass of, or a charge of 15. On this side, I have a charge of 15. So I don't need to account for any charge. What particle that we've seen has a mass of 1 and a charge of 0? If you said neutron, you're correct. So this would be an example. Now we've got two reactants. So that means it will be artificial transmutation, but plus it also gave out a neutron. So we're going to label it that way. I'll do one more with you, then I'll ask you to pause it and come back and check your work. So on this one, we have 214 bismuth. On the right, we have 4. What's missing? 210. On the left, we have 83. On the right, we have 2. What's missing? 81. So go check your periodic table, find atomic number 81, and you will find that it is TL. And if you look at that picture, what's missing? This particle, and we have an alpha decay. So please pause the video, try these next problems, and come back, and then we will look at the answers together. Welcome back, ChemStars. Let's take a quick look at your work. You might have got a little confused down here. I stopped giving you the atomic number, but you have the ability to figure that out by using your periodic table. So remember, the key in all of these is to conserve mass on both sides of the arrow and to conserve charge. I'll see you in the next video. Bye, guys.